So our first problem today, we're going to draw a shear and a moment diagram for a 6-meter beam. This beam has a wall at the left end. There's a roller 4 meters away from the wall. There's a uniform distributed load across the entire length of the beam. And you're also told that E and I are constant. So the very first thing we need to do is draw a free body diagram for this beam. We have a couple reasons for that. First, we need to figure out if this is going to be a determinate or an indeterminate beam. So we're going to reveal our free body diagram. On the left side, we have two perpendicular forces that represent the complete translational restraint given by the wall. I've called them F1 and F2. There is a rotational restraint represented by M1 from the wall. So again, that wall restrains all translation and rotation. And then the roller is represented by its vertical restraint, and I've called that F3. So if we look at what we have in our free body diagram, I have 4 external unknowns. Right? I have one free body diagram which has 3 independent equations of equilibrium, and so this beam is 1 degree indeterminate. So we're going to need another equation beyond those 3 equilibrium equations. So the way we're going to solve this is 2 ways. First, we're going to use the second order beam equation as our 4th equation. Second way we're going to do it is by indeterminate superposition. So the second order beam equation is the curvature proportional to the moment. So again, what we need in there is the internal moment. We need what's going on inside the beam, and that's going to relate to something we can see on the outside of the beam, and it's proportional through E and I. So what I need is that internal moment. So I'm going to go back up here to our whole structure free body diagram, and so what I'm going to do is I'm going to cut this beam open, and so I'm going to cut it, and I'm going to cut it at a distance x. And when I cut it at a distance x, and in this case I've defined my x coordinate going from the left to right, I'm going to end up with 2 free body diagrams. I'm going to end up with one on this side and another one on that side. So if you wanted to pause and go ahead and do that, you can do that on your own and draw your internal forces. The solution to that looks like the following. On the left side of the beam, again at a distance x, what I've exposed are all the internal forces. Axial, which is P, shear is V, and moment M. And these all adhere to our beam equation sign convention. And on the other side of the beam, again, I have the same internal forces, just equal and opposite. And what I have left is 4 meters minus x, and also my 2 meter overhang. So at this point, we'd want to evaluate what we need is m of x. So what's the best way to go about doing this? And for an indeterminate beam, what we're going to find is, as we see from our picture here, our internal moment is going to be a function of those external support forces. Right, those red arrows. So I'm going to choose to use the free body diagram on the right because I'm going to solve for the moment in terms of only a single red arrow. That actually is the force that we're going to solve using the beam equation. The quickest way to do that is I'm going to sum moments at the cut. And if I sum moments right at the cut, right there, I'm going to spin a moment. I'll call clockwise positive to do that. And so what results is the moment m of x got a contribution from the red F3, right? That's the roller force, again with its lever arm. And then the other thing that has happened is I have now chosen to represent the distributed load as a statically equivalent load, right? Its value being 2 times 6 minus x. And so you see that here. And then its lever arm to the cut would be 6 minus x over 2. And so now I'm just going to go ahead and shuffle that around. And so I've got m of x now. And I'm going to do just a little bit of math on that because I'm going to get this thing in a little bit nicer presentation here. So I'm going to have all my x squared terms. I'm going to have my x term. And then I'm going to have all my constant terms. So that's my function m of x. And again, what we notice from a indeterminate beam is that the moment is a function of the external support. In this case, I've again chosen F3 from the free body diagram side. So we're just about ready to start our beam equation, but what we're going to need to define is our boundary conditions. Because again, as we integrate our second order beam equation, constants of integration are going to start coming forward. So if we look at our beam, and again defining x going from left to right, also the transverse deflection v is defined positive upward. So our physical boundary conditions over here at the wall, I would know that v at 0 has to equal 0, so the transverse deflection is 0 at the wall. I also know that the first derivative of v with respect to x, which is the slope, that also is remaining at 0 throughout the entire problem. And the other boundary condition is sitting at that roller, so I know that v at 4 has to equal 0. So again, noticing that I have 3 boundary conditions here for our indeterminate beam. So all we're going to do is now head down to beam equation. And again, I'm just going to put the moment that I found above right in for m of x. So there's our second order beam equation. And so what I want to do now is start integrating. So if I integrate this, I end up with slope, and then we see that we've raised the order of all of our terms. There's our x. Now the x goes to an x squared goes to x to the third, and we have a constant of integration that's shown up. And so at this point, we would make a decision as to should we apply a boundary condition. And it would make good sense to do that because we have a slope boundary condition. It happens to be at 0. And so I know that the slope at 0 is defined with all the values of x equal to 0. And that then shows up right there in our equation. So this kind of simplifies nicely. I end up with a bunch of zeros plus c1 equals 0, which tells me that c1 equals 0. So what we've just solved for is right back here. We've just solved that c1 equals 0. So I'm going to take my slope equation and I'm going to integrate it one more time. Now I have an equation for v, which is the transverse displacement. So again, you see that x to the third has become x to the fourth. Right? Our x squared has become x to the third. Right? We've got x's now at x squared, and we have another constant of integration that I've called c2. Right? And now we have 2 boundary conditions that we're going to apply. I'm going to choose v at 0 first. So again, all I'm going to do is plug in x equals 0. That's going to zero out all those terms. And I know that the deflection at 0 equals 0. So very nicely, c2 equals 0. So all we've done is just found that that equals 0. And so if I just now rewrite my equation, right, this is the transverse deflection. However, I still have an unknown in there. I've got F3. But we would know that we have our third boundary condition. I know that V at 4 has a value. I know that that's going to equal 0. So if I reveal, I'm just going to take my deflection equation and just going to plug in 4 for x. And so that's what you see here. And I know that V at 4 has to equal 0. And so at this point, this just becomes a solving exercise. I'm going to put all my F3 terms on one side, all my constants over on the other. And now I find that I get a value for F3. And so that value is positive 8.5 kilonewtons. And so that means that F3 is equal to 8.5 kilonewtons up. And again, in the original free body diagram, we drew F3 pointed up. So that's what my positive answer relates to. So what we've just created is a free body diagram that now looks like this. And so when we first had 4 external unknowns, and again 3 equations of equilibrium, now we have 3 external unknowns that we still have not solved for, but we've turned the roller force into a known by using the second order beam equation, a kinematic equation. So let's just kind of take a look at what we've got here. If I just take V of x and I'm just going to plug in the value for F3 that I found. And so then it just becomes a little bit of a math exercise. I can do some simplification. I can write these things out slightly different. And so the other thing that I've created here now is an answer for the entire profile. However, this is from 0 to 4, right? Only between the wall and the roller. Outside of the roller, we're going to have a different equation for m of x and a different equation for v of x. Right? Likewise, if we go back and look at our moment equation after we cut the beam open and solve for it, where we had F3 that was sitting in there. So again, I'm just going to go plug in what that value of F3 was, which was 8.5. So that reveals my equation for m of x. And if I just go ahead and simplify that, I now get my expression for m of x. Again, however, this is only for x from 0 to 4 meters. Right? We go ahead and look back down here at our solved free body diagram. So the beam equation gave us quite a bit of information about our beam in addition to the value of that roller force.